Welcome to another OU Space Science Club talk. It's great to see so many here, and thank you very much for giving up your time again on a weekday evening to come and watch another one of our talks. My name's Ian Muirhead. I'm the outgoing chair of the Space Science Club, and Tracy, who's just been mischiefing me about being muted. She's the incoming chair, so it's great to have her there. Give everybody a wave, Trace.
Hi, guys.
There we go. I'm sure you'll see plenty from her. So this is my last talk, and I'm really pleased and honoured to be doing it. Before we go into the talk, I just want to go through a bit of administration. So tonight's talk, as always, is recorded. And the main talk will be recorded itself, but the question and answer session won't, so I'll stop the recording later on. Please keep your mics muted during the talk, and if you turn your cameras off as well, that'd help. The talk itself should be around 45 minutes long. Hannah will be dead enthusiastic, so if it goes on, we'll absolutely forgive her, and I've got time for it. For the Q&A session itself, once we've finished and stopped the recording, we'll go into that, and it'll either be a format of I'll pick your questions out of the chat, so please make use of it, or we'll get you to put your hand up and you can ask your questions of Hannah yourself. So that's it for the administration, and to go on to the talk then. So firstly, welcome Hannah, and good evening.
Hi, how's it going, everybody? Good to see you all.
There you go. Yeah, we've got loads of people really enthusiastic coming to see you tonight. And the first thing I want to say, and it's a good bit of closure for me as my last talk, is people might not know, but Hannah was indirectly fundamental in the formation of the club. So I was with a number of fellow students from S818 last year. We were at the National Student Space Conference, and Hannah was on one of the panels. And when they announced her as a OU researcher, everybody cheered in my course, but there was about 5 or 6 different groups cheering across the room, and everybody was, who are these people? How do we not know you're here? And that's why we decided to form a space community. So indirectly, Hannah was instrumental in forming it. She is a member of the club and supportive of us. So it's really great to have her to come and do a talk and tell us about her research and to come full circle for me. So thank you very much for giving up your time, Hannah.
No, it's an absolute pleasure. It's great to see how far the club has come, actually, and it's an honour to be invited to do a talk for you.
Brilliant. Well, we love your Zoom game, love the rocket in the background as well. If you've got control now, so hopefully you can share your slides, and I look forward to the talk.
Excellent. Right, let's give this a go. Is this starting to share?
Yep, that's good. I can see your slide.
This is not looking. Hold on. So you can see just the slide. Is that right?
I can see mine in the moon, just the slide title slide.
Okay.
Yes.
Okay, so my screen's doing funny things, but we'll go from here. Okay, so I'm going to be talking about mining the moon, in particular something called ISRU, or In-Situ Resource Utilisation, and I'll explain what that is. So here's a bit of a rundown of what I'll be going through. So I'll talk a little bit about my background and how I ended up doing what I do, an intro to ISRU and what I mean by that, and in particular lunar water as a resource for space exploration. And then I'll talk a little bit about the history, about lunar water and its discovery and what it means, and then how we might extract that water to give us oxygen. And then I'll talk a little bit about ISRU instruments and different missions, in particular how my research is related to those different missions. Including there was a study that I did looking at boulder hunting on the moon, and I swear it's related. But I really enjoyed that project, so I wanted to tie that in. And then a bit of a summary of everything, and then I'll show you just some really cool resources that I really enjoy using that are free to use and that you might want to have a go with at home as well. Okay. So a little bit about me. Well, I was originally a physicist, so I did my BSc in Sheffield. I started in 2010. I didn't do that great. My head really wasn't in it. And although I really love science, I realised, well, I thought I could, a career in academia wasn't really for me. And so I ended up training and working as a teacher. So I got my PGCE at Loughborough University. So I was training to teach physics and maths and science in general. And then I worked as a teacher before I kind of realised that I wanted to give academia another go. And so I ended up doing my course in space exploration systems at the University of Leicester. And it's there where I really found that this is what I'm passionate about and this is what I'm good at. And I learned so much about everything to do with space exploration, whether that's systems engineering, astrodynamics, rocket science, literally, planetary science. And I was also introduced to the concept of ISRU and using resources in space. And so I ended up looking for PhD projects that might include that sort of thing. And there was only one project that came up, and that was at the OU. I didn't even realise the OU did research or did PhDs, but I'm really glad that I found out that they do. So I've just finished my PhD in planetary science with a bit of space instrumentation in there. And it basically means I've spent the last 10 years driving up and down the M1 from Sheffield to Loughborough, Leicester, and now Milton Keynes. So yeah, let's tuck into the meat of this talk. So to begin with, the moon. What is it? Well, it was formed from the impact of what we believe was a Mars-sized planet that hit into a proto-Earth, and all of the debris from that was orbiting the Earth sort of came together and formed the moon. And as it started to cool, it formed a crust, and that's where this light material, the lighter grey material, which we call the highlands, was formed. And then the lower areas, the basins, they filled with molten material from deeper down within the moon. And this was richer in iron and titanium, and that's what gives it this darker colour. And it's called the mare because ancient astronomers believed that these dark areas were seas on the moon. And mare is Latin for seas. So in terms of exploration, there's been quite a few missions to the lunar surface, but mostly in this equatorial region. So, and most of them as well on the near side. So we only ever see this face of the Earth, this face of the moon from Earth. And so it's much easier to send missions to the near side because we have direct line of sight for communications. There was a recent mission to the far side, the Chang'e 4 mission, but we also haven't really explored the polar regions of the moon either. So there's lots more for us to go and explore. So now, how does ISRU come into this, in particular in relation to the moon? So ISRU is the concept of using local resources to support current and future missions. So by that, I mean, for example, if you're on the moon, you could use the regolith, which is this upper layer of rubble and dust and dirt. You can use that to build habitats, you can build roads and landing pads, you can also extract resources from it to build infrastructure and a whole plethora of things. But one of the most important resources that we might need is water, and in particular hydrogen and oxygen, so the constituents of water. And that's because hydrogen and oxygen are used as a rocket propellant, and rocket propellant gets used in large amounts and very quickly. So if we were to launch everything that we needed from Earth, it would become it would just be too costly. It wouldn't be worth it. So we need to be able to produce resources on the moon to support missions on the moon, and produce resources on Mars to support missions to Mars. But there's also another concept, and it's the idea of using the moon as a stepping stone to Mars. And by that, I mean producing some of the resources such as propellant on the surface of the moon and launching that into space. And then you can rendezvous with the crew that launches from Earth and then travel onwards to Mars. And then when you get to Mars, you could produce more resources whilst you're there, including the propellant you need to bring yourself home again. And one of the reasons why, or the main reason why this is a consideration for future exploration, is because of something called a gravity well. So here's a nice little comic from XKCD explaining what a gravity well is. And it's basically the amount of energy that you need to use to escape the gravity from that planetary body. So you can see that you need a lot of energy to escape the gravity well of Earth, because Earth is so much bigger, so gravity is a lot stronger. Whereas on the moon, the gravity well is smaller, so you don't need as much energy to escape the moon's surface. So this is why it took a huge rocket to get us to the moon, but only a small one to get us back. So if we can produce the resources that we need, such as propellant on the moon, it won't take a lot of energy to launch those supplies into space. So ideally, we want to launch as little as possible from Earth. And so if we can produce other things on the moon, then that'll be really helpful. But the problem is the moon isn't exactly well known for its vast supplies of water or hydrogen and oxygen. So where are we going to get this from? Well, there was no evidence of water in Apollo samples for many, many years. More recently, there was evidence of smaller, tiny amounts of water, but nothing particularly meaningful in terms of using it as a resource. There's also no mica, clay minerals or hydrous iron oxides, and all that means is that these are things that form when there's water present. So if there's none of those minerals, then it means there likely isn't any water. I'm just going to mute this person. Also, there's no water alteration found. So that means that there's no evidence that water has, or like flowing water has been present. So a nice example of this is this image. This is a zoomed in photomicrograph, or basically it's just looking at really close in to some samples. So we've got a lunar sample on the left and a sample from Hawaii on the right. And this sample from Hawaii is from a relatively fresh eruption that hasn't really interacted with water. And you can see they look extremely similar, showing that these lunar samples just haven't really had those interactions with water at all. But there is a suggestion that there could be water in what we call permanently shadowed regions, or PSRs. So these are shadows in craters in the polar regions. And because the sun is so low in the sky, it means that no matter what time of year, there are certain places at the base of these craters that will never ever see sunlight. And that makes them extremely dark and extremely cold, and act as cold traps. So if any water molecules are ever present or nearby, they will stick there. Whereas everywhere else on the moon, being in the relatively, pretty strong vacuum, any water will vaporize effectively. So it's only in these cold traps where, let's say, a meteorite or asteroid or comet strikes the surface. If it has some water molecules on it, some of those might stick in these PSRs. And over time, we think there are some pretty large deposits of frozen water in these polar craters. And so we sent a few missions to try and search for this water. So these are orbital missions, and they found evidence of hydration, that meaning it's either water or just OH in the polar regions. And they've tried to map where these water deposits are, and they align pretty nicely with these shadowed craters in the poles of the moon. Here are some maps of the polar craters here, with the blue spots showing us where there is some hydration. But there's lots of evidence from these orbiting missions. So there's evidence for an increase in hydrogen, which suggests that there's water there. They've measured the temperatures, and they show that these areas are suitable for stable water to be present. They reach as low as like 30 Kelvin, so really, really cool temperatures. And also another piece of evidence, which is quite interesting, is that they were able to look at the albedo, which basically tells us how reflective the craters, the surface of the crater floor is, and it basically suggests that it's quite frosty on the base of some of these craters. But in terms of direct evidence, because we haven't landed anything in one of these polar craters before, we did do, well, there was another mission that I thought was a really cool idea, and it's called the LCross Impactor, and they basically sent a spent rocket stage, so an empty rocket stage, and they basically dropped it into one of these shadowed craters, and there was this trailing spacecraft that was able to detect what was released in the plume from the impact, and water vapor was detected. So this was the first piece of evidence directly that there is water in these polar craters. But what if we can't get to the polar craters? Because it's not exactly easy to get into these places. How else could we get water on the moon? Well, the main thing that we're actually interested in with regards to water is the oxygen. So in H2O, the O is the heaviest part significantly compared to the H, the hydrogen. So we're really interested in getting the oxygen because it's not cost effective to launch all of this oxygen from Earth. And actually, there is a lot of oxygen on the moon. It's just bound up in the mineral structure. So around 40% of lunar rocks is actually made up of oxygen. So here we've got just some of the common minerals that you might find. I wasn't really a geologist before I started, but I'm learning. So we have pyroxene, feldspar, olivine and ilmenite. Don't need to know what they are. But basically, you can see in red here, we've got all of these oxygens bound up in these minerals. So how would we extract it? Well, there's a bunch of different chemical reactions you can use. One of them that I'm quite familiar with now is hydrogen reduction of ilmenite. So ilmenite is one of these minerals. And basically, if you put hydrogen into a system, you add some hydrogen and you heat it up to pretty high temperatures, around 1000 degrees C, you produce water. So the hydrogen bonds with the oxygen in the mineral to produce H2O. And if you have a cold trap nearby, what we call a cold finger on our machine, that water will stick there, and that means we can trap it and store it. And what is produced is iron and titanium dioxide, which is effectively the waste product. But iron and titanium are also really important materials in buildings and building, like, well, tools and all sorts of different things. So there are many uses to these other sort of products of this reaction. And in terms of performing this sort of experiment on the moon, we haven't done it yet. We haven't been able to do any ISRU on the moon to date, but there have been some sort of test runs. So back in 2012, there was this study that was released on some work being done in the US. So they had some sort of prototype rovers and landers doing these sort of ISRU experiments to extract oxygen from material in Hawaii, because we know some of the material in these Hawaiian sort of eruption plains is quite similar to material on the moon. And they were really successful, but unfortunately, until very recently, ISRU work didn't really get consistent funding. But aspects of these different prototypes is being worked on and carried forward at the moment. And I couldn't go on without mentioning the first ISRU experiment that has ever been performed. So this is a really recent advancement. So you might have heard of the Perseverance rover. Well, I hope you've heard of the Perseverance rover, and on board is something called MOXIE. And this instrument produces oxygen from the atmosphere on Mars. So because Mars does have an atmosphere, it gives us another option of how to get oxygen. So it basically turns the CO2 that is present into oxygen. And it's able to make around 10 grams of oxygen per hour. It's quite a small scale demonstration, but this is the first step. So by showing that this is successful, it means that larger scale demonstrators can then be developed. So which one is best? Going back to the moon, is it best to go to the polar craters, or is it best to get water, or, well, oxygen from the dry regolith material? Well, in the polar craters, we think that these are pretty large deposits, so you could go there and have quite a large supply of water to extract, and it's pretty easy to extract. You apply some heat and that water should be released. But they are found in really hazardous areas. They are so cold, some places thought to be less than 30 Kelvin, and that means you have to produce technology that can survive in those areas. Because they are permanently shadowed, there's no direct solar power, so you need to think about how you're going to get power to your equipment to extract the water. And also, you need to be able to access the bottom of some craters. Now, notoriously, rovers don't like to go anywhere particularly steep. They like to go to nice flat plains. So how are you going to get equipment into these locations? Whereas if we're looking at getting water or oxygen from the dry regolith material, one of the benefits is that you can do these experiments or these extraction techniques pretty much anywhere. The moon is pretty homogeneous in terms of how the material is distributed, which means you could go somewhere nice and flat and easy to access with nice communications to Earth. But these extraction techniques take a lot of energy. They're really complex and they take a lot of resources. So you might need to bring quite a few different supplies from Earth to enable for these reactions to continue to work. But what that tells us is basically there's no right answer. Depending on other aspects of your mission will dictate which technique you'll use to supply the oxygen and the water that you're looking for. So this brings me on to the work that I've been involved in over the last few years, and this is related to the ProSPA instrument, but it's part of a payload that's been made by ESA, European Space Agency payload, and it's flying on the Lunar 27 lander, which you might know is a And this lander should be heading to a south polar location of the moon. And what's quite special about this mission is that it's going to be looking for frozen water, and it's going to try and make water from the regolith itself. So it's going to look at both aspects of getting water and oxygen from the moon. So a little bit about the history of how this instrument has come to be, mainly because being OU students, a lot of you, it's kind of nice to look back at the heritage of the work that the OU teams have been working on. So the GAP instrument was an instrument built by the Open University, and it's flown on Beagle 2, which headed to Mars. Unfortunately, it landed on Mars, but some of the panels didn't open correctly, so it wasn't able to communicate with Earth. So we think it's still there. It'd be really cool to go back and see what state it's in at the moment. But unfortunately, it wasn't able to collect any data with regards to the instrument that was built. And the instrument, or the GAP instrument, is a mass spectrometer, or as part of GAP is a mass spectrometer. So this is the payload that was built at the OU. And basically, it's designed to take in some samples into these miniature ovens, these little ovens here. I don't know if you can see my mouse, but anyway, so the idea is that a sample will be collected, deposited into the machine, and these little ovens would heat up, and any sort of, I guess, vapors that are released can then be detected by a mass spectrometer. Now, the OU team that I've been working with then kind of took this concept and applied it to the Rosetta mission. So Rosetta landed on Comet 67P, and the Ptolemy instrument is what was built by the OU, and this involved building another similar setup. So it has some ovens there, sort of in the middle of the box, these little circles. So the ovens would, well, the goal was to get some samples into these miniature ovens, heat them up, see what was released, and detect it with the mass spectrometer. Unfortunately, the mission, the lander landed at a funny angle, which meant that the drill couldn't drill down into the surface material to take a sample. And so instead, the team decided to open up the mass spectrometer to the environment. Now, when it landed, it released a lot of sort of debris into, I guess, this sort of atmosphere, I suppose. And some of that debris was able to fall into the mass spectrometer, and that was able to be detected. They called this sniffing mode. And using this concept, they actually came up with a cool little instrument that's going to be heading to the moon, which is called Pittums. So this is the ProSPA ion trap mass spectrometer, and it's flying on an astrobotic lander, I believe later this year. And it basically was like it's like a really stripped back version of these mass spectrometers that they've been working on. And it basically just has like a door that they will open up, and when they land, anything that is kind of released upon landing might fall into this mass spectrometer and can be detected. For example, we could look at how the exhaust fumes get distributed when it's landing, and how long those rocket fumes might last, might sort of hang around, and what damage that might do to any sample collection. So that's kind of the development of these mass spectrometers. So how does that fall into this kind of ProSPA design? So as part of the ProSPA lab, the ProSPA kind of instrument, we have this miniature lab, which has the mass spectrometer on board, amongst other things. And we also have the sample collection section. So this has a carousel of ovens at the bottom. And here we have a nice video. And so the concept is we'll land somewhere near the poles. The ProSPA drill will drill down into the surface of the moon, collect some samples inside the drill. Here's an example of it kind of being tested. I believe this is out in Italy. So we deposited into this sort of funnel. It will collect down into some of these miniature ovens, and then those ovens will be heated up, release some volatiles or some vapors, and the mass spectrometer will tell us what we've found. And hopefully, if there's any water present, we'll be able to detect that for the first time with a lander on the moon. So then I came in as a relatively fresh-faced PhD student, and I was told that this is what the ProSPA instrument is going to do. Now, can you do any other ISRU experiments? And so I was given this this sort of engineering drawing of what the rough kind of ProSPA design was going to to be. Looks a bit overwhelming, but I kind of took out from it the key components that I really needed. So we have an oven in the bottom left. We have a cold finger at the bottom right where we can trap some water. We have some hydrogen, so we've got a little H2 canister there in the middle, and we've got a mass spectrometer. So I pretty much have everything I need to do that, that hydrogen reduction experiment that I mentioned earlier. So that's what I wanted to test. Can I do that with the ProSPA instrument to produce water from the dry regolith? So the first thing is to look at, well, we need to make make a machine in the lab to run some of these tests and see can we make it. So we had in this sort of rough schematic of what I was aiming for in the lab, it was just the key components that I needed. So a cold finger, a furnace, a hydrogen supply, various pipework to connect it all together, and a mass spectrometer on the outside. This sort of the big red dashed box is basically I needed to put everything in a hot oven because basically water sticks to everything. It sticks to all of the pipework. And I wanted to make sure that the water was only going to stick in the cold finger. So the cold finger was kept really nice and cool with liquid nitrogen, but everything else was heated up. So this is what I ended up building. This is about 2 meters wide. It's a pretty big beast that we've ended up making, and this is because it's made from commercial off-the-shelf parts or COTS. So it's just stuff we can buy easily online. So we've got some sort of pretty basic insulation board to make this hot box. We've got some oven heater elements at the bottom and some chicken wire to keep us from burning ourselves. But it meant that I had the equipment I needed to check if this experiment would work. So what was I aiming to do? Well, I had a furnace that could get to the right temperatures of around 1000 degrees C, and I would put some ilmenite or whatever other samples I wanted to test in there, some interconnecting pipework called the manifold, and then the cold finger on another side of the system that I would cool down to pretty cool temperatures, about -80 degrees C, to trap any water. So I would put some hydrogen in there. That hydrogen would then sort of fill out into the whole system, and any hydrogen that came into contact with the hot ilmenite would convert into water, and then those water molecules would diffuse and sort of fill out into the rest of the pipes, and if any of that water struck the cold finger, it would stick there and condense, and I would trap it down. And as that happened, I should notice a pressure drop. So as I was running these experiments, I would be measuring the pressure, and if I could see a pressure drop, then I was pretty confident I was producing water. I could then turn on the vacuum, pump away anything else that's gas in the system, close it off, heat up the water, and I should be able to see a nice pressure rise from that release of water from the cold finger. So these were the two things that I was looking for in my experiments to check that I had made water. And the other thing I would do is I would actually then take those samples out, polish them down and look at them with microscopes, or scanning electron microscopes we call them, to see how the reaction, if I could see evidence of the reaction in these grains of ilmenite or whatever else. And what should happen is these minerals should start to produce these bright white streaks, which tells me that it's basically that iron has formed. So as this iron forms, it's telling me that the experiment has happened, the oxygen has been removed, and I've produced water. So these are all the different things I was looking for. So after I was able to kind of show that it worked with ilmenite, and then I started looking at, is this actually going to be possible with lunar material? So to do that, you start off with a simulated material. So there's a lot of different simulants, like lunar simulants, that you can access. So I had access to this particular one here on the left. It's called a lunar highland simulant. I then also had access to a meteorite. So this is a piece of the moon that got launched into space after a giant impact, and some of that rock then fell to Earth. So you can purchase these, and I would crush some of this down into a powder and then react that as well. And if those were successful, then I was given access to some Apollo soil. So I had a sample from Apollo 11. So this was the contingency sample that Neil Armstrong collected. And then I also had access to an Apollo 17 sample because I wanted different types of soils to check that how the experiment compared between different locations on the moon. And so I won't show you any data because no one likes graphs, but everyone loves images. So here is some of the polished images that I had of the simulant. So this is before I reacted it. So this is what the grains look like in the fake moon soil. So I've got all these different minerals in there. And then when it reacts, you can start to see, if I have an ilmenite grain, these lovely bright iron streaks were found. And this matched up with the other evidence that I had. And even some of the other minerals as well, if they had some iron oxide in there, some of them would also react and produce some iron. So it would show me that these types of material we find on the moon could be reacted using this technique. So this was really promising. And then I had to go with some lunar soil. So here's some cool images of some lunar soil grains. And lunar soil forms like some really cool cool shapes. So because there's no atmosphere, the moon is being bombarded by impacts all the time, and so the soil is constantly being broken down and melted and reformed, and that's why you end up with these really these mixed grains with loads of different minerals sort of mixed together. And then after the reaction, bit of a mess, but basically here's a nice bit of ilmenite in one of the grains, and we had some iron streaks forming inside. So this told me that I was able to produce water from actual moon soil. So hopefully this reaction will work when we fly this mission in around 2025. So since I finished working on that project, so that was for my PhD, I've continued to work at the OU now as a postdoctoral researcher, and I've been working with the LUVMI-X rover team. So this is a Lunar Rover concept, and it's designed to head to the polar regions of the moon, which is why it has vertical solar panels, because the sun will be quite low in the sky. And it's a kind of similar concept to the stuff I've been working on already, in that it has a drill on board. It will be drilling down, collecting a sample. It has a mass spectrometer, so that's going to be trying to detect water in those samples, but it has the benefit of being mobile. So it's able to explore a lot bigger regions on the surface to see how the water concentration might change over sort of larger distances. And another cool idea is that it has these little deployable payloads with mass spectrometers in as well. So we could drop off these little detectors, go and explore some of the things and then come back. And it also has a deployable, so it can launch these little detectors into craters. So you don't have to send rovers into these hazardous regions. Instead, we can launch something in there to make this much safer. And this brings me on to the other project that I was involved in, which is looking at how to access these polar craters. So I've mentioned, we don't really like the idea of sending rovers into craters, but what if we did want to send something in there? What would that material be like? So we wanted to investigate, can we safely enter these PSRs to explore the resources that might be there? And this is a project I did as a graduate intern at the Lunar and Planetary Institute. So any undergraduate or postgraduate students can access different internships in Houston with the LPI. So I would recommend looking into those. And in this study, we were looking at trying to understand the strength. Let me go back here. It was trying to understand the strength of the soil. So there was a concern that inside these polar craters, the regolith might be very porous and very soft, and that rovers might sink when they go in there. So what could we do to investigate the strength of these polar craters without sending something there that might, hundreds of millions of pounds, that might ultimately kind of get lost as soon as it enters the crater? And so we were introduced to a concept, which is the idea of using Boulder Tracks on the moon to measure the soil strength. And this is something that has been done since before the first moon landings. So they had some images of the moon, and they would look at boulder tracks on the surface and try and figure out how strong that soil was to help design the moon lander, because they didn't know if the moon lander would sink meters into the soil. And so here's some nice images of some of the boulder tracks you might see on the moon. Boulder tracks are actually quite common. They can be the result of an impact releasing, chunks of rock, and they will fall down slopes. Perhaps they might shimmy down after a moon quake, which are things. So we were looking at measuring these boulder tracks and measuring the boulders and trying to see how far they sink in to see how strong they are. So we used this free-to-use website. It's called Elrock Quick Map, and what it does is it gives you all of the images from the Lunar Reconnaissance Orbiter camera, and they're really super high resolution. They're really like the most recent images of the moon. So we could filter them down and figure out and basically try and find boulder tracks in and around these polar craters. So the first thing was, can we actually see boulders near to these craters? So if we find one, generally you can find more. So here's a boulder track that we spotted near to one of these PSRs. But there's actually another one in there. I don't know if you can see it. So here's another little boulder track. We found ourselves looking through so many images. We were spotting boulder tracks in our sleep, I think. But this is a tool that we use not just to look at PSRs. We're looking at lots of different regions of the moon to compare all the different results. But how are we going to actually look inside these craters? I mean, they're black, they're dark. How on earth do we see inside? Well, if you look at PSRs from a certain region in the poles, there is just enough sunlight reflected off the rim of the crater that gives you this sort of secondary light into the shadowed areas. And by doing some sort of manipulation of the images, play around with the contrast and brightness, and then someone in our team developed this really awesome filter, suddenly you can see to the bottom of these craters. So you can see there's a bit of a sort of a landslide formation going to the bottom of these of this PSR here. And this was really awesome because we're literally looking into places that have never seen sunlight or direct sunlight in millions of years. Here's a nice zoomed in image of one of the filtered look inside one of these PSRs. And at the base here, you can see loads of boulders. So the question is, can we actually find some tracks along the edge of these craters? Well, the first thing we did was trying to find tracks going into the shadows and see if we could basically play around with it and look at the tracks inside. And here we can see a track that had gone from the outside and into this shadow. And what was really interesting is that the track size doesn't really change much. So as a sort of a qualitative study or analysis, it's looking like these PSRs look pretty sturdy and can handle these boulders rolling through. It's not like the boulder suddenly sunk as soon as it ended up inside these shadows. And basically what we found after running a bunch of these calculations and various different measurements that we were taking, we found that the PSRs are actually slightly easier to traverse on than the other areas of the moon, like the highlands and the Mare regions. So this was really exciting, and it was reassuring to the engineers designing these rovers. And it means that the rovers should be able to traverse these areas without sinking. But the main thing that we learned is that boulder hunting is hard. You can have a go, but it is it will send you loopy. So here's a nice little track that we were able to spot and take some measurements from. So the next steps in terms of sort of accessing resources on the moon is summarised quite nicely in this global exploration roadmap. So this was produced by a team called the ISECG, and it's kind of like all the major space agencies kind of focusing on where are we heading in the next few decades. And so the goal is in the very near future is looking at prospecting missions. So this is the stuff that I've been involved in, trying to identify the locations of ideal resource deposits that we might want to target for the next step, which is the large scale resource extraction technique. So producing tons of oxygen, tons of water to produce the rocket fuel that we need, also to support a base with the life support resources and so on. And so, yeah, we need to be able to then integrate all of those resources into actual missions, into crewed missions in particular. That would be really exciting. And then ultimately being able to launch some of those supplies into space to support, say, missions to Mars. So in summary, what we've been learning and what I've been involved in over the last few years, we've come to find that water is super critical to future space exploration. And that it can actually be found on the moon, or if we can't go to locations to sort of dig it up, we can actually make it there instead. The ProSPA instrument being developed at the OU could perform one of the first demonstrations of water production on the moon, which would be very, very exciting. And we've also learnt through the LPI internship work that we can use remote imagery to prepare for some of the exploration of these PSRs for digging up water. And ultimately, we are one step closer to living off of the moon. Now, before I finish up, I'm almost there. I just want to mention these 3 different things that you can use at home. So Google Moon, you might have heard of. It's an offshoot of Google Earth. It's a great way looking kind of back in time. So it's great for looking at sort of really old maps of the moon, like geology maps of the moon made pre-Apollo, and then they have some really great tours and links to imagery and videos and so on from the Apollo missions. There's also Elrock Quick Map, which is what I mentioned, looking at the most up-to-date imagery of the moon. So you can, it's so good. You can even see like the Apollo landing sites and see some of the tracks that were left there from the rovers and such. And you can also look around in 3D. And there's another one which is called Moon Trek, which is quite similar. Excuse me. You can actually plot traverses on the moon, and it will. And if you have VR headsets, for example, it will. You can produce your own sort of virtual tour using actual images of the moon. And this sort of technology is ultimately going to be used to support astronaut training, as to help them sort of plan their routes on what they're going to be doing on the surface of the moon. I did a brief kind of video about a couple of those things if you want to have a kind of get stuck in, because some of them are a bit complicated to get started on, but just have a Google, and if you want to have a play around, I've got a few tips. But I think I'll leave it at that. It's a lot of information, but if you've got any questions, please send them my way. So thank you very much.
Thank you very much, Hannah. That was a really great talk. I absolutely loved the link between all the past OU missions and involvement in space research. And I think that absolutely meets one of the aims of the club. We set it up to try and link a distance learning student body with some of the great stuff that happens in the OU. And I think you've absolutely sold that. And the chat's going absolutely mad now with people saying awesome and thank you and loving it. So yeah, it was brilliant. We're going to go on to a question and answer session first, but I just want to wrap everything up and close up before we stop the recording for those watching later on the YouTube channel, or in fact those that might have to leave now. So for everybody watching online, thank you very much. And for everybody in the chat now, our next talk is on Monday the 14th of June at 7 o'clock in the evening, and it's Dr Megan Argo from the University of Central Lancashire, I think, and she's doing astronomy in the next 200 years, which will be a great talk. That'll be launched, I believe, tomorrow afternoon, and one of our committee will launch that on Eventbrite. So please get yourself signed up, and we'd love to see you there. So that's the end of the talk. Thank you very much, and there should be some subscribe, share thing here going on YouTube. Please do that and comment. Let us know what you think about it. See, there's Tracy waving her hands around as well. And we'd love to see you at future talks, but thank you very much and good evening.